Many of us learned from an early age that charged matter interacts. Like charges repel, opposite charges attract. And our discussions in this course so far have centered around these notions, fleshing them out in a bit more detail using the concept of the electric field. However, this is not the full story. You may be surprised to learn that there are many examples in nature where matter has zero charge and yet can still interact electrically. Let's explore how this can happen. First, however, let's do a quick review by trying to answer this question. 3 electrons are fixed to the locations on coordinate axes as shown. Each electron is the same distance from the origin. Choose the numbered arrow that best represents the direction of the net electric field at the origin due to these 3 electrons. If you think the net field is 0, choose answer 9. Pause this video and give yourself a bit of time to answer the question before continuing. Here's the solution. The net field is the superposition, the sum of the electric fields at the origin due to each electron. We can represent the field of each electron at the origin by an arrow. For a given electron's field, the arrow will have its tail at the origin and point toward the electron as shown. Since all 3 electrons have the same magnitude of charge and are the same distance away from the origin, the arrows for the fields will have the same length. We can add the arrows graphically, head to tail, to find the net electric field. And what we see is that net field points in the plus y direction, which is best represented by answer number 1 on the rosette of arrows. Now we know the stuff with which our world is made is built from atoms, which in turn contain charged particles, most commonly negatively charged electrons and positively charged protons. So, quite commonly, matter will actually have a total charge, a net charge of 0. We call that matter neutral, because that piece of matter has the same amount of positive charge as negative charge. Now, matter that has a total charge of 0 is still able to interact electrically, chiefly because the positive and negative charges can be at different spatial locations on or within a piece of neutral matter. We've already seen an important example of this, the electric dipole, in which equal amounts of positive and negative charge are separated in space. In some dipoles, this separation between the positive and negative charges is locked in place. We call these permanent dipoles. A water molecule is one such example. The oxygen and hydrogen atoms bond together in a stable configuration that has a net charge of 0, with more positive charge closer to the hydrogen atoms and more negative charge closer to the oxygen atom. Recall that we can characterize the dipole by the vector dipole moment, vector p, where the direction is described by the unit vector p hat that points from the negative charge toward the positive charge. The magnitude of the dipole moment of a permanent dipole is a fixed quantity. For a water molecule, it is measured to be approximately 6 × 10 to the minus 30 coulomb meters. You'll recall that we can write the magnitude of the electric dipole moment as a product of the magnitude of either charge, which we will write here as capital Q, times the separation distance S between the positive and negative charges. For the water molecule, We can think of capital Q as equal to 10 times the elementary charge E, since there are a total of 10 protons and 10 electrons, where the magnitude of the charge on each proton or electron is equal to E equals 1.6 times 10 to the minus 19 coulombs in SI units. In this case, we can compute the separation distance between the average position of the positive and negative charges in a water molecule, like this, which works out to be about 0.04 times 10 to the minus 10 meters, which is a tiny separation in comparison to the water molecule size. The separation is about 2 orders of magnitude smaller than the linear size of a water molecule, which is around 1 times 10 to the minus 10 meters. Nevertheless, clearly, this piece of matter, overall charge neutral, can interact electrically, as we discussed earlier. The dipole produces an electric field, something like that shown here, which can, for example, exert an electric force on a charged piece of matter. Here's another way neutral matter can interact that you may find more surprising. Let's consider a piece of matter that is neutral, where the positive and negative charges contained in the matter have the same location, on average. Here's one example: an atom where the electron cloud is spherically symmetric and centered on the nucleus. Classically, we would expect the electric field to be zero at locations outside this object. However, if the atom is placed in an external electric field, a field due to some other charges not shown here, for example, then it's often the case that the neutral object polarizes. The positive charges shift in the direction of the external field. The negative charges shift in the direction opposite to the electric field. In other words, the object becomes an electric dipole. Unlike the water molecule, this dipole is not permanent. If the external electric field goes away, the dipole character of the object goes away. This is an example of an induced dipole. The dipole is induced by the presence of an external electric field. The induced dipole has a vector electric dipole moment where, as you might expect, the direction is described by the unit vector p hat that points from the negative charge toward the positive charge. Moreover, as you might expect, the magnitude of the electric dipole moment could be written as a product of the separation distance between the positive and negative charges and the magnitude of either charge. In this respect, the vector dipole moment is the same for either induced or permanent dipoles. However, there is a big difference here. The electric dipole moment of an induced dipole is not a fixed quantity like a permanent dipole. The dipole moment of an induced dipole depends on the external electric field at the location of the induced dipole. The simplest way to write this is as a constant alpha times the external electric field, where alpha is a material property called the polarizability, with the units in the SI system of coulombs squared meters per Newton, which is typically a positive quantity. This expression tells us that the direction of the vector dipole moment of an induced dipole is always in the direction of the external electric field, and that the larger the magnitude of that external electric field, the larger the magnitude of the dipole moment for the induced dipole. So let's summarize. Dipoles are an important example of neutral matter that can interact electrically. We've seen here that there are two types of dipoles, permanent dipoles and induced dipoles. In both cases, the vector dipole moment describes the dipole character, with the direction given by p hat and the magnitude described as the product of the separation between the charges and the magnitude of either charge. The dipole moment of a permanent dipole is fixed. However, the dipole moment of an induced dipole depends on the external electric field applied at the location of that induced dipole, which we can express as this product of the polarizability alpha times the vector external electric field. For an induced dipole, if there is no external E field applied, there is no dipole. In our next lecture, we will work an example showing how we can calculate electric interactions involving an induced dipole.